Happy Monday, young physicists. I am here again. Schedule meet at 9:05. Is this too early for you? If 9:05 is too early for you, leave a comment in the Google Classroom and let me know what time would work for you. But anyways, no one's here yet. Oh, there's Arturo.
What's up, Mr. Frank? I was just in Mr. Frank's class, and now I'm in physics. I'm good, Mr. Hennings. How are you?
Good, good. No, I get it. You gotta kind of bounce back and forth. What time would be good for you, Arturo? Is 9:05 or is that time good, or do you think it would be better to do another time?
Just because there's a couple of us in pre-calc and maybe other periods, I think maybe like 9:45 would be a little better, or maybe even 10.
Okay.
9:45.
Well, I'll ask the students. I'll ask them to post on the classroom what time, and we'll try to pick a time that works for the most people, right?
For sure.
How are things going with you, Arturo?
It's not bad. It's good. We got the food. I think we got everything we need, and it's just a matter of staying indoors now.
Yeah, it is, huh? You're doing really well in terms of. I was checking classes. You know, progress reports go out, and I was checking all the students' progress. It looks like you're doing well. Isolated there by yourself.
Yeah, it's been cool. I get to spend more time with my family, like my little brother and my little sister. Like, we're not too guided by. Well, I don't know. It's just really cool to spend time with them and really feel like an older brother. Because I'm always like in Sierra or I was running cross country and track. It's cool to spend time with them. They're like growing up, and I had never noticed.
Yeah, that's great. I mean, you gotta find the positives, right? In terms.
Yeah, it's been good for sure.
Yeah.
So I wonder if anybody else remembers.
Well, I don't know. I mean, I posted it on the classroom last week. I sent them reminders. We'll see what happens. We're recording it, so we'll go forward. Do you have any questions about physics class first, Arturo, before we start?
No, I think I've been good, Mr. Hennings. All good.
All right. So I'm going to go ahead and get started, and hopefully, I'm going to record this, like I said, so if students miss it, they can figure it out. I'm going to share my screen, and you tell me, make sure that you can see it, okay?
Got it. Yeah, I can see it.
Okay. So we're looking at, let me see here. So this is all, I shouldn't keep you here too long. Do you see an agenda out in front of you, Arturo?
Well, yeah, I do.
Yeah. So I want to talk a little bit about the waves unit and what we're going to be studying initially, pendulums and masses on a spring. And then your assignment for today is going to be part of a gizmo. So you won't do the whole thing, but I'll show you what that assignment then looks like. All right. So the first thing I want to do is I want to pull up the grade book, and that's right here. And here's where what we're going to be really close to assessing. In fact, I'm going to push out this assessment tomorrow. So aspect 1 of the waves unit is given a diagram of a wave. Students can identify amplitude, wavelength, node, crest, and trough. So there literally will just be a picture of a wave, and you're going to label different parts of it, right? Aspect 2 will be a little bit more. There's going to be some calculations involved, and it says given sufficient information, students can calculate period and frequency. Given data and measurements, students can differentiate between periods and frequency. So this is something you've already started, and you're going to continue then today. The homework assignment or the problems that were given out of the book last week were examples of what that will look like, right? Oh, yeah. So stop sharing this one here. We'll take a look. What you're going to be working on then today is, can you see, Arturo, what you're looking at here? I got a little setup here with a pendulum and a mass on a spring. So both of these are similar, and in fact, the mathematics for finding the period and the frequency is going to be really similar as well. But both of these are what are referred to as simple harmonic oscillators. It means that they're doing something over and over. They're repeating, right? So a pendulum, we know, swings back and forth. And in the old days, that's how we used to keep time. A grandfather clock was just a pendulum of a certain length that would keep time for us. So that does a particular motion back and forth, and that would be called a simple harmonic oscillator. I'm going to pull this one off And then in the gizmos, you'll look at a pendulum, right? Kind of what's the physics that's important to it. And then this is a mass on a spring. And it does something similar. Instead of moving like a swing back and forth, if I disturb it, it moves up and down. But it repeats its motion also, up and down. And you can imagine it repeating, you know, I guess theoretically forever. So the gizmos is going to ask you to make some measurements and figure out what are the periods in the pendulum, or the periods and the frequencies of a pendulum and a spring. And you'll be asked to then do a little bit of an investigation as to what determines the period and the frequency. So for a pendulum, does it matter if I put a really big mass on it, a little mass, if I make it really long versus short, if I pull it back? What about for a spring? If I put a large mass on it, I use a stiff spring rather than a loose spring. That's what you're going to be investigating in the gizmos today, right? Okay. So let me just go ahead and then show you the gizmos. Give me a moment here.
This is awesome. This is straight up tutoring. I'm getting tutoring.
You're one-on-one, right? One-on-one, yeah. Arturo.
Shut up. I've been waking up early too. I think that's what helps with the keeping up. You said
are you exercising right? Still, Arturo?
I am. I actually.
Good for you.
You said you wake up at 4 or something, and that stuck to me. I was like, damn.
It's actually changed, and the gym's closed, right? So, like, right. I can't go to the gym anymore. I'm trying to do, you know, body weight stuff at home. Been out skiing a little bit, but it's tough.
Yeah.
All right.
No. Let's do it. What matters on the gizmo? Okay, cool.
So I'll show you here. Can you see the classroom, my Google Classroom on the page?
Yeah.
All right. So here's today's post. The objective is to demonstrate your knowledge of wave basics. We're at the Google Meet right now, and then I'm going to introduce the gizmos. If you're interested, Arturo, I did post Devin Ginty. He posted, you know, he's doing our week, kind of our, what do we refer to that thing? I've already forgotten the name.
Good morning.
Yeah, exactly. The announcement, a weekly announcement. So if you want to watch that, you can. So here's your assignment. It's up here, and I'll open that up and open the instructions. So I left you a link, right, to Gizmos. Hopefully you're going to be able to remember. You can get back on that one. And then here is the assignment. Now you'll notice what it says. It says Gizmos, simple harmonic motion, only sections A and B. So when I pull this up, make sure that you're not doing the whole thing. We don't need to do the whole thing for prep physics. There's a little bit here. Have you worked with this Cami before, Arturo? I can't remember if you did this one before. Yeah. So the same thing. You can put your answers in using Cami in that case. And the gizmo is going to have you look at a spring and a pendulum and just answer a few questions about that. Here's the important part moving forward in terms of what you're going to be quizzed on tomorrow. Tomorrow, you're going to be asked some questions that test, do you know how to calculate the period and the frequency of a pendulum and a mass? So they're going to be questions like that. If you can do this on the gizmos, man, you're going to do fine on that level 1 and level 2 assessment for tomorrow. So activity A just focuses on finding the period of a spring. And what determines it, you'll notice they're going to change the mass, the spring constant K, and the gravitational acceleration. So 9.8 is Earth. They'll check it on a couple different planets, a small planet with a 5 and a 20. And then activity B is something very similar, except it's dealing with the pendulum. And again, you're going to explore, how does the mass on the end of the pendulum affect its period? How does the length of the pendulum affect the period? And also, how does the gravitational acceleration affect the period? And you'll answer a few questions once you get some data for that. That's the end. Once you get to activity C, you don't need to do any more. Okay, so it's just activities A and B, and that should give you pretty good practice for the quiz that I'm going to push out tomorrow.
So there's no frequency on the gizmo? Or is it, did you say there was?
You don't have to do a frequency, right? But that really should be a really simple step, right? Can you? Are you seeing me now, Arturo?
Yeah, I can see you.
Yeah. Remember that the definition is those two things are related. So if period is capital P And that's all you're asked to find in the gizmos is the period. If gizmos is capital T, then the relationship is your inverse.
Oh, yeah.
Right. So if I know the period, I can just do this simple calculation to find the frequency. And the reverse is also true, right? Then the frequency must be 1 over period. So really, if you can find one, you know the other.
Okay, cool.
Right?
That's what I was struggling with on Friday's assignment of 6, 8, 9, and 10.
Okay.
I like halved it. I like did it, but not really understood it or anything. I didn't turn it in. So I was hoping we could just go over those problems. Is that cool?
Sure. You want to do one of those?
Yeah. So number 6 is, I have the book if you want to
just read me the problem, Arturo, and then we'll do it.
Okay, cool. So it's an air track glider attached to a spring oscillates between the 10 centimeter mark and the 60 centimeter mark on the track. The glider completes 10 oscillations in 33 seconds. And then from there, it's just like, what is the period? What is the frequency? What is the amplitude? What is the maximum speed of the glider?
All right, I'm going to set it up here.
So it seemed fairly simple. Like I was like, that's got to be like a super easy problem, but I
think it is simple here, but we'll solve a couple of them here. So first of all, it's kind of weird. What they're talking about is, imagine, like an air hockey table. Something like this is happening horizontally. So instead of the mass going up and down, there's a spring that's pulling like a hockey puck on an air table back and forth. Does that make sense?
Right. Yeah.
And they're telling us then that the way that it moves is, if I have here a little coordinate system, here's 10 centimeters and here's 60 centimeters, they're telling us it's moving like this, right? So it's moving back and forth like that. So what's the first question then they're asking about?
What is the period? And it gives you that it does 10 oscillations in 33 seconds.
10 oscillations in 33 seconds?
Yeah.
All right, so what that means is the period, you got to remember what that is. The period is the time it takes for one oscillation, one complete cycle. So we want the answer to be in time. We don't know, it doesn't tell us specifically about one cycle, but it tells us the time for 10, right? So the solution would look like this.
So is that 33?
33 seconds.
Divided by 10, right?
Divided by 10 cycles.
Dang it,
So then the answer is, with the period, I would report that as saying the period is 3.3 seconds. So, that's moving back and forth, kind of slow. 1, 1,000, 2, 1,000, 3, 1,000 is sort of the time frame that it's going here and back. So 1, 1,000, 2, 1,000, 3, 1,000. That's about how fast it's going.
Oh.
Now, I don't know, does the problem ask for the frequency too?
Yeah, it totally does. Right after B is frequency. So that's the reciprocal, right?
Exactly. That's the inverse. So I know that there's a glare on the screen I'm trying to get away from. So the frequency is just going to be 1 over T, and that's 1 over 3.3 seconds. So that ends up being like, we'll approximate it, 0.33 hertz, something like that.
.33, which equals 0.33, and then that's always hertz.
Yeah.
Okay, I don't know why I had 0.303, and I don't even remember how I got that, but either way, probably wrong. Okay, 0.33 hertz, and then amplitude is the amplitude. I wrote all the definitions down after watching the video on Friday. So amplitude.
It's a little bit different, right, Arturo? If you look at this, right, the amplitude. So I have the pen here. The pen is marking equilibrium, right? So the amplitude is the maximum distance away, above and below the equilibrium mark. So if I slow this thing down, right, that would be like its
Negative
amplitude, and then that would also be its maximum amplitude. So we're thinking its equilibrium section is usually going to be right in the middle, right? So what's happening, when the spring comes to rest, it's just going to rest right here. So what's happening is during its oscillation, it's going to a maximum displacement of 60 centimeters and then going to a minimum of 10. So it's going back and forth like this. So when it comes to rest, it's probably going to come to rest right here. So what can you determine? What do you think the amplitude would be if this is 10 and that's 60?
So from 10 to 60 is 50. I'm getting 25.
That's it. You got the right idea. Absolutely. 25.
Okay. 25. And then the measurement for amplitude is, in this case, would be centimeters, right? Yeah.
Absolutely. Yeah.
Oh, okay.
You're crushing it, Arturo. You're crushing it.
This is so much simpler than I thought.
Well, yeah. So treat those problems that were out of the book. I think a lot of people are going to probably struggle with those kind of as an introductory thing. And that was what today was about, for students to ask questions exactly like what you're doing. I think after this discussion, when you look at the gizmos, you're going to find those period and frequency calculations a piece of cake.
Got it. And then speed is probably the easiest one, right? Just the distance over time. And in this case, the distance would be from 10 to the 60 centimeter mark. So 50 over 33 seconds. Right.
Well, you got to remember, though, that that's happening. So let's just take a look at here what speed is. This one, that's going to be like aspect 3, Arturo, when we get to wave speed stuff. So it's okay if you're struggling with it now. But let's just figure out, what does this 3.3 seconds mean? It means that, serious glare here. The 3.3 means that you're getting, that it takes this long to go from 10 to 60 and back, right? That's a complete cycle. So the distance that it traveled during this 3.3 seconds, its period, is actually 100 centimeters. Does that make sense? It goes from 50 to 60, then 10 to 60, and then 60 to 10, and that takes 3.3 seconds.
Oh, okay. Okay.
So then the speed calculation is really simple. The distance that it went was 100 centimeters divided by 3.3 seconds. So it has an average speed of 30 centimeters per second.
And that was 100 divided by 33.
100 divided by 3.3 seconds. All right, it's just a distance divided by time.
And that's 33. Okay, and then that would be the maximum speed. So 33 centimeters per second.
We'll use that. It'd be an average speed, yeah.
Okay. Dang. Okay, cool. Thank you, Mr. Hennings. And then from there, the rest of the problems are the same thing.
Yeah, the rest of the problems are similar. So, like I said, I'm not too concerned about your performance on those 4 problems that I assigned, because they're just going to be the first time students see it. I think after you look at the gizmos, if you can do the gizmos and be confident with it, you're going to do fine on the assessment that I push out tomorrow.
Sweet. Thank you, Mr. Hennings. On number 10, it says to draw the position graph showing 2 cycles of motion. That's probably like what you just explained to me there, right? But it would be like a squiggly line.
It's going to be like a sign line. Read me a little bit about the information, and we'll sketch one out.
It says, an objective and simple harmonic motion has an amplitude of 6 centimeters and a frequency of 0.5 hertz. Draw a position graph showing the 2 cycles of motion. Amplitude of 6 centimeters. Okay, so 6 is the big picture.
We'll do that.
6 centimeters. Okay, cool. And then frequency of 0.5 hertz. And then frequency was...
All right. So, Arturo, can you see what I'm starting to sketch on the board there?
Yeah.
So here's my 6, right? We know we have an amplitude above equilibrium of 6, and then below it'll be -6, right, in terms of its position. The information in the problem says that the frequency is at, what is it? Half hertz?
Yeah, 0.5 hertz.
0.5 hertz. So then my first question for you, because what are we going to draw? We need to know the period to be able to draw the wave. So what would the period be if the frequency is 0.5 hertz?
So frequency is 1 over period. So the period would be the inverse of that.
That's right.
Okay, and then that would be T over this is the period.
It's going to look like this, right? T will be 1 over 0.5 hertz. So 1 divided by 0.5, what would that be?
2. Okay, cool.
It's 2. So what does that mean? It means that it takes 2 seconds to complete a cycle, right? So I'm going to make some timelines here. Here will be 1 second, 2 seconds. And does it say that how many cycles are we supposed to draw?
2 cycles of motion.
All right. So there's 2 seconds, there's 3, and there's 4. So this is time on this axis. So let's just put it together. That's one of the reasons I kind of like this question, is because you really have to understand a lot about the basic nature of waves. Amplitude is 6, so I can start my wave. I'll start it here. And a complete cycle, we just said, takes 2 seconds. So a complete cycle would be start, maximum, and then back. So then I know at 2 seconds it has to be back.
It ends in second. Okay, cool. Yeah. Okay,
at 1 second, it's going to be here. So now I can kind of sketch out what that sine wave will look like. And the same thing is going to be true at 4 seconds.
And then that's 1 and 2 cycles. Oh, okay, got it. Cool. Mr. Hennings, I get it.
Good.
Yeah, that's fine. Okay, cool. Thank you, Mr. Hennings. And apart from that, I think I got the rest.
Yeah, so email me if you got any questions, Arturo. And like I said, I'm doing my office hours still from 3 to 4. I only usually get a couple people at a time. So make sure if you got questions that you're asking, okay?
Got him, Mr. Hennings. Thank you.
All right. Arturo, thanks for stopping by. I'm going to post this video, so you're going to be the star of today's video for the rest of the students.
Thank you. All right,
man.
Well, I'll see you, Mr. Hennings.
All right, have a good day, Arturo.
Yeah, you too.
Bye.